Welcome to the 21st lecture in Abstract Algebra. The topics that we will explore in this lecture include using the fundamental theorem of finitely generated abelian groups and an introduction to permutation groups. Okay, so I'd like to begin this lecture by making a correction to the proof for the theorem in part 3 of the previous lecture. For those of you who have my notes, this is theorem 20.14. But first we need to start with an example. Let G be the direct product from I equals 1 to 5 of the groups of integers modulo m sub I, and let H be the direct product, the trivial group, times the integers modulo m sub 2 times the integers modulo m sub 3 times the trivial group times the trivial group. Then H is a non-empty subset of the group G. Now let X and Y be two elements in the set H where X is the ordered quintuple 0, A, B, 0, 0, and Y is the ordered quintuple 0, C, D, 0, 0. Now since A and C are elements in the group of integers modulo m sub 2, A plus the inverse of C is in the group of integers modulo m sub 2. And since B and D are elements in the group of integers modulo m sub 3, B plus the inverse of D is in the group of integers modulo m sub 3. And so X plus the inverse of Y, which is the ordered quintuple 0, A plus C inverse, B plus D inverse 0, 0 is in the set H. And hence H is a subgroup of the group G. Now let phi be a map from the subgroup H into the direct product of the integers modulo m sub 2 with the integers modulo m sub 3, and let this function be defined by phi of x, which is phi of the ordered quintuple 0, A, B, 0, 0, be the ordered pair AB. Then clearly the function phi is a bijection. Since for every ordered pair AB in the direct product of the integers modulo m sub 2 with the integers modulo m sub 3, there is exactly one quintuple that is mapped onto it. Further, phi of x plus y, which is phi of the ordered quintuple 0, A plus C, B plus D, 0, 0, is the ordered pair A plus C, B plus D, which is the sum of ordered pairs AB and CD, is phi of x plus phi of y. And hence the subgroup H is isomorphic to the direct product of the integers modulo m sub 2 with the integers modulo m sub 3. Now, in general, if G is the direct product from I equals 1 to n of the groups of integers modulo m sub I, then the direct product of the integers modulo m sub I with the integers modulo m sub j for I greater than or equal to 1, strictly less than j, and j strictly, or correction, less than or equal to n. This direct product is isomorphic to a subgroup of the group G. So now, as an example, we'll make the correction to the proof of the theorem in part 3 of the previous lecture. The problem was with the first implication. So if the group G, which is the direct product from I equals 1 to n of the groups of integers modulo m sub I, is cyclic, then the direct product, correction, then the integers m sub I for I in the range from 1 to n are pairwise relatively prime. So proof: suppose that the group G is cyclic, then every subgroup of the group G is cyclic. Now, since the direct product of the integers modulo m sub I with the integers modulo m sub j for I greater than or equal to 1, strictly less than j, which itself is less than or equal to n, this direct product is isomorphic to a subgroup of the group G, and so it is cyclic. And so the greatest common divisor of the integers m sub I and m sub j is 1, where once again I is greater than or equal to 1, strictly less than j, which is less than or equal to n. That is, the integers m sub I are pairwise relatively prime. Okay, so now we're ready to look at the exercise from the previous lecture. So let G be the direct product, the integers modulo 4 times the integers modulo 12 times the integers modulo 15. First, we are to find the order of the ordered triple 3, 10, 9 in the group G. Now the order of the element 3 and the integers modulo 4 is the order of the group, which is 4, divided by the greatest common divisor of 3 and 4. This is 4 divided by 1, which is 4, or 2 squared. The order of the element 10 and the integers modulo 12 is the order of the group, which is 12, divided by the greatest common divisor of 10 and 12. This is 12 divided by 2, which is 6, or 2 times 3. The order of the element 9 and the integers modulo 15 is the order of the group, which is 15 divided by the greatest common divisor of 9 and 15. Which is 15 divided by 3, or 5. And so the order of the ordered triple 3, 10, 9 in the group G is the least common multiple of 4, 6, and 5, which is 2 squared times 3 times 5, or 60. So part 2, we're to determine or find the max order of an element in the group G. Now the maximum order of an element A in the integers modulo 4 is 4, which is 2 squared. The maximum order of an element B in the integers modulo 12 is 12, which is 2 squared times 3. And the max order of an element C in the integers modulo 15 is 15, which is 3 times 5. So the max order of an ordered triple A, B, C in the group G is the least common multiple of 4, 12, and 15, which is 2 squared times 3 times 5, or once again 60. So part 3, we need to determine, is the group G isomorphic to the direct product of the integers modulo 20 with the integers modulo 36. Now the max order of an element A in the integers modulo 20 is 20, which is 2 squared times 5. and the max order of an element B in the integers modulo 36 is 36, which is 2 squared times 3 squared. So the maximum order of an ordered pair, AB, in the direct product of the integers modulo 20 with the integers modulo 36 is the least common multiple of 20 and 36, which is 2 squared times 3 squared times 5, which is 180. So since the direct product of the integers modulo 20 with the integers modulo 36 has an element of order 180, and the group G does not, the group G is not isomorphic to the direct product of the integers modulo 20 with the integers modulo 36. Now we can also solve this problem using a different route. Notice that the integers modulo 15 is isomorphic to the direct product of the integers modulo 3 with the integers modulo 5, since the greatest common divisor of 3 and 5 is 1. And so the group G is isomorphic to the direct product, the integers modulo 3 times the integers modulo 4 times the integers modulo 5 times the integers modulo 12. Now since the greatest common divisor of 4 and 5 is 1, the direct product of the integers modulo 4 with the integers modulo 5 is isomorphic to the integers modulo 20. And so the group G is isomorphic to the integers modulo 20 times the integers modulo 3 times the integers modulo 12. However, the direct product of the integers modulo 3 with the integers modulo 12 is not isomorphic to the integers modulo 36, since the greatest common divisor of 3 and 12 is 3, which is not 1. And so the group G is not isomorphic to the direct product of the integers modulo 20 with the integers modulo 36.